Hello, welcome to another video on financial math for Actuarial Exam 2, also called Exam FM. My name is Bill Kinney. Here's my profile picture on my YouTube page as of the 1st of December 2017. For the vast majority of these videos, we've looked at doing a bunch of problem solving from two books for the most part. The Mathematics of Investment and Credit, 6th edition by Samuel Broverman, and The Theory of Interest, 2nd edition by Stephen Kellison. Though in a few recent videos I've also done some sample problems from a sample Actuarial Exam 2 from 2017. And in this video I'd like to do something different. Now in the very last video, number 115, we looked at bond valuation methods between coupon payments. In this video I want to compare them. In that last video, video number 115, the main focus was on the main method, the semi-theoretical method, which is the most common method. That's the method that, at least as of 2017, you should know if you are taking Actuarial Exam 2. I did also briefly mention another method called the practical method. There's a third method called the theoretical method that I want to go over in this video as well. But I think that's going to be the end of talking about bond valuations between coupon payments, because I want to get onto Chapter 5 of Broverman's book, which gets into things like the internal rate of return on an investment, net present value, that kind of thing. And as far as solving problems in this area goes, it's pretty straightforward. You just use the formulas that you should remember. In this video, you can see it's a pretty long video. I'm going to do something else. I'm going to do something that is going to be pretty challenging, but I think it'll be very worthwhile. We are going to compare the different bond valuation methods with this program that you see here. It's called Mathematica. It's going to be definitely useful because the calculations would be very painstaking to do by hand. It'll also make nice graphs for us that we can animate. You don't have to understand the Mathematica code. You want to understand the concepts behind what I'm talking about here. The Mathematica code will help make the concepts come alive, I think. And I think it will definitely be worth your while, but you're probably going to want to have some paper out, pause the video every so often, write down some calculations, check what Mathematica does. It might take a little while. Make some graphs on your own. It's going to be a pretty challenging video, even conceptually too, but I think it will be worthwhile. So I hope you'll like it. What we're ultimately going to note in comparing these methods is the semi-theoretical method, the most common method, is actually less accurate than the other two methods, and really a bit strange, especially from a graphical point of view. Okay, so it is the most common. It seems fairly logical if you just think about it purely symbolically, but both numerically and especially graphically, it's actually a bit strange. It's a strange interpolation method, you might say. We'll think about this in the context of a particular example because it will help it seem more concrete. And again, this video is going to be difficult enough as it is. So here's the situation. Right here, we've got a $1,000 par value bond with semi-annual coupons, redeemable at par in 10 years. So you're going to be able to redeem it at $1,000. 10 years with semi-annual coupons, that's going to be 20 coupons. We're going to suppose that the annual coupon rate is 10% convertible semi-annually, which would of course mean that the effective coupon rate, effective semi-annual coupon rate would be half of that, 5%. And I'm going to let J, as I've usually done, be the effective semi-annual yield rate. Notice the word effective here. This is a semi-annual rate, so the annual yield rate would actually be 2J convertible semi-annually, but I will focus on just J being the effective semi-annual yield rate. If you're not sure what this is all about, you're going to want to learn more about bonds before you come back to this video. Maybe watch a bunch of my earlier videos. So, alright, so now we're going to get into some equations and some graphs. What we've usually done and what we do in this subject overall is we think about, well, the price when you buy the bond, but maybe also the value of the bond, the book value, typically just after a coupon payment has been paid, like 1 second later. So we're going to think about a coupon payment time t in half years, but t is going to be a non-negative integer, a whole number, 0, 1, 2, 3, 4, 5, etc., up through 20. These are in half years. This is not a time in years. It's every half year. Just after the coupon payment has been made, the value of the bond at the given yield rate is the present value of the future payments, not including the payment that just happened. Here's the basic formula. If this is unfamiliar to you, that's a clue that you're going to want to study up on this before you watch the video. I am using the basic formula here. Sometimes we just call this the price. I'm going to go ahead and call it BV for book value. Kellison's book calls it just B. But I'm going to call it BV sub T, where T is again a whole number, 0, 1, 2, 3, 4, 5, etc. F times R, as usual, is the coupon payment, which is 50 in this case. Think about that. That would be $1,000 times 5% would be 50. C is the redemption amount. It's redeemable at par, so there's 1,000 there. You've got your annuity immediate symbol here. So this is going to be the present value of all the coupons right there. And this quantity is going to be the present value of the redemption value. V, as usual, is the reciprocal of 1 plus j. It's 1 plus j to the negative 1 power. I am doing an arbitrary t here, 0, 1, 2, 3, etc. We often do this with t equal to 0, so often you see an n here and an n here, but if t is bigger than 0, then this could be something less than n. And you can use the formula for this thing to go ahead and make this replacement. Again, recall that v is 1 plus j to the negative 1 power, so instead of a 20 minus t power here on the 1 plus j, you'd reverse it to a t minus 20 power. Same thing over here. Okay? So I'm about to now use this formula to make a graph. In this program Mathematica, again, you don't need to know this code here. This just makes a graph that looks pretty nice for this given situation. There we go. And so we've got the book value as a function of time, discrete values of t. You can see whole numbers, 0, 1, 2, 3, 4, 5, 6, etc. It's a constant function of time here. When j, which I'm leaving in general unspecified, happens to be the same as 10% divided by 2, it happens to be the same as the effective semi-annual coupon rate, you get constant book values at these whole number values. That's something you should recall. You're buying the bond then for the same as the face value, the same as the redemption value. What happens now as j increases or decreases? I can use this slider up here and see what happens to this graph. But think about it first. If j, the yield rate, effective semi-annual yield rate, increases bigger than the coupon payments, you can intuitively think of that as the coupon payments are small with respect to the yield rate. You're not getting much in the way of coupons. You're not really getting a good return on your investment until the redemption amount at the end. So as sort of compensation for that, you would hope you would pay less than the face amount, and that is indeed what happens. You buy the bond at a discount when j is bigger than r. And it gets more extreme the bigger j gets, and I've allowed myself to go up to a really big value of j here, up to 0.5, which would be 50%, and you can see the extremeness in the behavior of this graph is very, very large when j is large compared to r. On the other hand, when j is less than r, now you can see up here at time 0 the price is high, you're buying the bond at a premium, the coupon payments are relatively high compared to the yield rate, so you're kind of getting a lot for your money at first, and sort of as compensation you got to pay more at first for the bond. Again, you can think of this as in terms of you loaning the corporation or government entity money and they are paying you back on the loan when you buy at a premium. In a sense, it's kind of like you're giving them more than what they were asking for or something. Their coupon payments, they are paying you more than just interest at the end of every period. And that does pay down their balance, so to speak. It amortizes it. And on the flip side, you're sort of loaning them less than they may have asked for in a sense when it's bought at a discount, and their coupon payments are not enough to cover interest, and so their balance goes up over time, and at the very end, at time 20, they would pay $1,000 to pay their balance off. Okay, so this is kind of neat. You can change j and see those changes. You can play this, though that's not super relevant in this context in Mathematica here, but it is kind of neat that you can see those changes. That's pretty powerful. All right, next we're going to go on to talking about these different methods for figuring out the book value between coupon payments. I didn't really talk about the theoretical method in the last video, video number 115, but I am going to talk about it now. What is the theoretical method to obtain the so-called clean price? Actually, in the last video we said it was the quoted price, though I mentioned that was a synonym for clean price. All these words, clean price, quoted price, book value, market price, are basically taken to be synonyms for this quantity. And what you do with a theoretical method to get the value between coupon payments based on this method is you essentially assume this equation is true when t is any real number between 0 and 20. You think of this as a continuous function of t. That's not the way most textbooks describe it at first. I'll talk about the way textbooks describe it in a minute. But let's just see in this graph that you are essentially just taking the discrete graph from the last picture and making it continuous. Okay, and once again, if j is bigger than r, then you get an increasing and concave up graph, and if j is less than r, you get a decreasing and yes, technically concave down, though it's only slight when j is real large or real small. It looks almost straight there, but it is slightly concave down. When j is exactly equal to r, 0.05, which I'm not quite able to get to there, then you have a horizontal graph that is straight. So that really is, in essence, what the theoretical method does. Now, in books, you'll often see it described this way. If t is taken to be an integer between, say, 0 and 19, and k is any real number between 0 and 1, take an arbitrary number between 0 and 20 and represent it as t plus k. Then the formula above, this thing right here, can be written like this, and this is the way you're going to typically see it, for example, in Kellison's book. You should check on your own that these are equivalent. This thing actually is something called the dirty price, okay? I'm not going to say quite what that is yet right now, but you're essentially taking the book value after the preceding coupon payment, right 1 second after it, promoting it forward in time, k years, k is a fraction of a year, or in this case a half year I should say, using essentially compound interest, okay? This quantity right here is, technically speaking, if you want to be real precise about it, the theoretical or maybe exact accrued value of the next coupon payment. I'm not going to get into what that means right now, but that's the way most textbooks describe it, and they show the formula this way. You should take the time to check that these formulas are equivalent. Okay, they are, though the equivalence is a little tricky because here t is any real number, whereas here t is a whole number, and you're taking the form of an arbitrary real number to be t plus k. That arbitrary real number would have an integer part, a greatest integer part of t, and a fractional part of k, you might say, and because of that, it makes the equivalence of these two things a bit tricky. All right, now what I'm about to do is something kind of strange, but I think worthwhile to think about. I think it will give you some insight into what's going on here. So we looked at the continuous graph of BVT with a theoretical method and saw that it was constant, horizontal, when j was equal to r. It was decreasing and concave down when j was bigger than r. That's when you buy the bond at a premium. Increasing and concave up when j was less than r. You're buying the bond at a discount. What I'm about to do is a little weird, but I think, again, still informative if you think about it carefully. I'm going to make some graphs of, first of all, the derivative of BV with respect to t. And actually, I'm going to think about it in terms of this BV formula. And the second derivative of BV with respect to t. So think about what that's going to give me. That's going to give me information about the slope and concavity of this graph. Those are derivatives with respect to t. But I'm going to do this, I'm going to make graphs of these things as functions of j, which sounds pretty weird, but technically speaking, since both j and t can be thought of as variables, I could do this. Notice the partial derivative symbols. These things are both functions of j and t as well, and I can graph them as functions of j, but then for different values of t. I'm going to make an animation as t varies, a slider for t, and see graphs of these things as functions of j for different values of t, and we're going to try to understand what it tells us about the original graph. We're going to also see that as t increases, so that in this graph you move to the right, the slope and concavity are more strongly affected by changes in the yield rate j. So I'm going to have Mathematica compute the derivative for me. You can check this by hand. There it is. You should note that in Mathematica, capital LOG actually means natural log ln. So when you differentiate this thing, that's something I would recommend doing, pausing the video and differentiating this with respect to t. You're going to get a natural log of 1 plus j involved, and that's what this log actually means, is natural log. So there's the derivative. You should be able to simplify to this. Now let's now graph this as a function of j. This code, you can see, well, it does plot it as a function of j because of this right here. But ultimately, for different values of t, this part right here is going to allow t to vary from 0 to 20. Don't worry about the details of that. And we get kind of a strange looking graph. How is it relevant here? Listen real carefully, okay? So we've got, notice first of all that this graph of the derivative of bv with respect to t has a horizontal intercept, and this is a j-axis, at 0.05 it appears. Okay, that's what it seems to be, at least. What is that telling us? Assuming this is 0.05, it's telling us that the slope of the original graph at time 0 at least is 0 when j is 0.05. The slope of this graph at time 0 is 0 when j is 0.05. And you can see, yeah, if I had an exact 0.05 in here, which I can type in, but it's actually a little funny when I do that, you get a horizontal line. The slope is 0. And that intercept is going to stay the same even if I increase t. Watch it. I'll increase t here. The intercept of this graph still stays at 0.05 effectively. So that's telling you, and I hope it didn't change it. It looked like maybe it changed a little bit there, but I'm going to assume it's staying there constant with an intercept at 0.05 for j. And what that's telling you is as t changes, as you move to the right on this graph, the slope stays at 0. Okay, because the intercept here for this derivative, the slope of bv graph at j equals 0.05 is 0. So when j is 0.05, if I imagine increasing t, the slope stays at 0. Now think about a value of j bigger than 0.05, whether slightly or much bigger. The value of this function is positive. The value of the slope of bv with respect to t is positive, not only at t equals 0, but at other values of t. When j is bigger than 0.05, like this, say, the slope at 0 is positive, and so is at 0 positive at other values of t. The graph is increasing. That's what that's telling us here. It's also telling us something more subtle. When j is close to, well, about 0.11 or so, the value of the derivative of the other graph with respect to time, the slope, is at a maximum when j at time 2.56. Let me go back to time 0. When t is 0, the maximum slope of the original graph occurs when j is close to 0.1. So look back at this original graph. I vary j bigger than 0.05. Notice that the slope when j is close to 0.05, right at t equals 0, is very close to 0. It gets a bit bigger as j increases. Evidently, the slope at time 0 here is biggest right around in here when j is close to 0.1. That's when the slope here is biggest. And it does go back down towards 0 here as j continues to increase. You can see the graph gets flatter and flatter at t equals 0. That's pretty cool. That's pretty significant, at least if you like thinking about graphs like this, thinking about rates of change. This graph goes back down as j continues to increase. It's got a maximum when j is close to 0.1. On the other hand, when t is bigger, like say we take t to be close to 8, then the maximum of this graph when j is bigger than 0.05 is more like 0.14 or 0.15 or so. That means back up on this graph, the slope when t is close to 8 is going to be maximized when j is close to 0.14 or 0.15. Now that's difficult to tell for sure. At t is close to 8, the slope right about there is maximized when j is about this much. It's tough to tell just by looking at the picture, but we are trusting what that derivative graph is telling us there. It's also telling us that when j is less than 0.05, The slope at any value of t, determined by the value of the red graph over here, is negative. J is less than 0.05. That's when you buy at a premium. The graph is decreasing with a negative slope. The slope does get more and more negative at any value of t, including at 0, as j continues to decrease. There's no local minimum over here, evidently. And that does happen. The graph doesn't flatten out like it did here. It's very flat right there. As j continues to decrease here, it seems like the slope is getting more and more negative. Okay? So the graph down here really is telling us that. It's also telling us, again, that as t increases, as I move to the right on this graph, the slope is more strongly affected by changes in j, and you can definitely see that, for example, as j increases. The slope for large values of t has more variability, you might say, is affected more by changes in j, okay, than the slopes are over here. We've also got another graph, another calculation to calculate the second derivative. There's code that calculates the second derivative. By the way, d is what calculates the derivative, and I'm doing it with respect to t and simplifying. You should check on your own that this is the second derivative. Log again means natural log. We can plot the second derivative as a function of j as well. It's pretty interesting too, somewhat similar. The only difference is that instead of for this part going down, evidently maybe to minus infinity, it goes back up to 0. That's telling us that no matter what t is, seemingly, the second derivative of the original graph, when j is really close to 0, that second derivative, that concavity, is close to 0. And that's what we see over here because the graph is pretty flat. When j is large here and t is close to 0, well, t could be actually, yeah, when t is close to 0, the graph over there is pretty flat. We did again see for other values of t that this graph comes back over here. That's essentially telling you that when j is really close to 0, the concavity everywhere is pretty close to 0 now. Yeah, okay, because the graph is pretty straight when j is close to 0. Yep, looks almost like a straight line. So this is telling us pretty useful information. I guess I should also emphasize it's telling you the graph is concave up when j is bigger than 0.05 and concave down because this is negative when j is less than 0.05. Telling you pretty cool information, very subtle information. You know, if you kind of got that, but you want to rewatch it, go ahead and rewatch it. Go back to when I first started talking about this and think through it as I described. I think it's pretty cool. And I think it's informative and could be important in real life when you're thinking about bonds and these different interpolation schemes. All right, I'm wanting to get on to the comparison between the three main methods, which are the theoretical method, the semi-theoretical method, and the practical method. Again, the semi-theoretical method is the main one to use on exams. The practical method's pretty simple, though at least in 2017, it's evidently not something you need to know for actuarial exams. The theoretical method is maybe technically the best method, most accurate, but again, in 2017, you don't need to know it. I want to compare those, but before I get there to the comparison, I want to show you the typical types of pictures that you see in textbooks that relate the clean price, which we've been talking about here, to the so-called dirty price. Now, what is the distinction between these things? The clean price, again, could be thought of as sort of just an interpolation of the values of the bond at coupon payments or right after coupon payments are made. The dirty price is actually the amount of money that changes hands between buyer and seller, at least, well, if the current yield rate is the same as the original yield rate. Now, yield rates can change, and that does affect how much money changes hands as well. But if the current yield is the same as the original yield rate, then the dirty price is the amount of money that changes hands. And it's essentially trying to take the accrued coupon into account. You know, if you sell the bond to somebody just, you know, a few days, say, before the coupon payment, they are getting the whole coupon payment, but you might be saying, well, I almost got to the coupon payment. Shouldn't I get some of it too? And so they, in a sense, need to pay you more for the bond because it's just a few days before the next coupon than they would if they bought the bond from you right after the coupon payment. So that's the dirty price. And so let me go ahead and enter this code and look at the picture here. This is a common kind of picture you see in textbooks, maybe one or the other of these graphs. What we're looking at here, the bold graphs, the blue and the green graphs, are clean prices. I labeled those with CP here. The blue one is at a premium, J is low, it's decreasing concave down. The green one is at a discount, J is high, it's increasing concave up, just like we already saw. Pick particular values of J here, it's not an animation. But then you see these dashed lines, the reddish ones up here and the magenta pinkish colored ones down there. And you see if you thought of those things as defining functions of time, they would be discontinuous. Those things are graphs of the dirty price, actually. I'm not going to get into how I made them, but just think conceptually with me here. Focus on, say, t equals 7. At time 7, the blue and the red graph agree right there. That's right after the coupon payment at time 7. The blue graph goes down because you're just connecting the dots here between t equals 7 and t equals 8. The red graph, the dirty price, goes up. It's taking the accrued value of the next coupon payment into account. It's going up until right before t is 8. It's 50 units because the coupon payment here is 50 above the point down here. Okay, so right before the coupon payment, the value is $50 higher than right after the coupon payment. That's the idea. So you get jump discontinuities there. DP stands for dirty price. Those are the dash ones. So this is a common kind of thing you see in textbooks, and you can think about it either with bonds bought at premiums or discounts in the same kind of way. The jump discontinuity is the same as the coupon payment in both cases. Okay. But what I want to do for the rest of the video is I want to continue to focus more on the bold curves here, not the dash ones, thinking about the different interpolation methods. And let's now talk about the practical method. Practical method to obtain the clean price. It really is a pretty simple concept. We're just taking the BV values at integer values of t, positive integer values, whole numbers, and we are interpolating, linear interpolation between those. Formula is typically written either like this or like this, where once again t is a whole number and k is a real number between 0 and 1. You get the value at t plus k to be an interpolation of the value at t with the value at t plus 1. Think about this kind of equation when k is 0, for example. This is 1 and this is 0, so the value is bvt. On the other hand, at the other extreme, when k is 1, this is 0, and this is 1, so the value is bvt plus 1. And in between, if you graph this, it gives you a straight line. Alternatively, you can write the formula like this. You should check that. This, once again, like before, is the dirty price now. But now it's with simple interest, it turns out. This is the k is not in the power, it's the multiplier of the j in here. That makes this simple interest, and if you recall, simple interest does give you straight line growth. That's the dirty price there. This is the accrued coupon. It's a simpler pro rata growth, it's called, proportional growth in the accrued value of the next coupon. You can just see it's proportional to k. When k is 0, it's 0. When k is 1, it's f times r. And in between values of k, like 0.6, it's that percentage of f times r. When you subtract these things, you get the clean price, which is, in America at least, the things that's quoted on the different trading boards. I guess in Europe, they often quote the dirty price, from what I've read. Anyway, this is the clean price, this is the dirty price, this is the accrued coupon, and this subtraction gives you the same thing as that, and you should check that. Okay. What about the graph of this thing? I'm going to have Mathematica graph it. Now, there's some technicalities in doing this in Mathematica. You can actually do it in various ways. The way I'm choosing to do it is based on taking an arbitrary real number and taking the greatest integer in that real number, that's in Mathematica is called the floor function, and then taking its fraction apart and adding them. And using essentially this formula here along with the floor and the fractional part, as you can see here. But don't worry about the details if you don't care about them. So the graph looks like this when j is 0.05, and in fact for other values of j it really doesn't look that much different than the other graphs we saw, but there is a subtle distinction that Mathematica seems to be making. If you look carefully here, you do see little gaps between these pieces of the curve at integer values of t. Actually, the true graph doesn't have gaps, but the true graph is piecewise linear. These are all straight lines, and they're going to be connecting to each other with different slopes. So technically speaking, this graph being piecewise linear like that, except when j is 0.05, it's not differentiable everywhere. It's not differentiable at the whole number values of t. You're just connecting dots with straight lines. That's a little bit more apparent if you zoom in a little closer, as I do with this graph. We're zooming in closer. You can see the subtle differences in the slopes. Positive slope, slightly bigger slope yet. These are straight lines with different slopes, and we have points where the derivative does not exist. The function is not smooth at the points of where the whole number values of t, where you have these changes in slope. But it is, for the purposes of computation, certainly a very simple method and certainly probably pretty accurate. Now we're on to the semi-theoretical method, which again I talked about in video number 115 and we made use of as the main technique in that video, and the main technique you should know for Actuarial Exam 2 in 2017, and maybe in the future. How do we obtain this? We do the pro rata increase in the coupon amount, but we use compound interest for the growth in the preceding book value after the preceding coupon payment. It seems pretty logical, you know, why not do that? Why not use compound interest here and a simple pro rata proportional increase in the accrued coupon value here? It's pretty logical, but what we're going to see is, if you look at it real carefully, there are some weird things that go on. The full graph is less accurate. It doesn't always make a big deal if your dollar amounts are small, but it is technically less accurate because it's just strange. It's a strange interpolation, as we're going to see. This programs it into Mathematica, and now I can look at the graph, and on a large scale you can't really tell a difference. It is piecewise, like the practical method was, and so you see tiny little gaps here in this picture, even though in reality there are not gaps. They're not holes in the graph. You need to zoom in further to see the strangeness that occurs, for example, between t equals 4 and 8. The graph actually decreases sometimes, even when j equals r, and so you should be saying, well, shouldn't the graph be just horizontal? And when j is slightly bigger than 0.05, it's got places where it actually decreases. It's definitely not differentiable at the whole number values of t, not smooth, but even more strangely, at least if j is close to r, it's got portions where it decreases. If j is large enough, it's no longer decreasing, but it still is kind of strange. You know, why would you connect the dots with this kind of interpolation scheme? On the other hand, when you buy the bond at a premium, it's still strange. And once again, when j is close to 0.05, well, in this case, you would think the graph should always be decreasing, but now you've got little pieces where it's increasing, which is kind of strange. Okay? So it's a strange method. Now, can we understand why it's doing this? I want to get there. Before I get there, let's compare all these methods with zoomed-in scales. We'll see that the difference between the theoretical and practical methods is negligible, while the semi-theoretical method has a significant aberration from those other two graphs. Most people would probably call it the semi-theoretical method, both inaccurate and strange. It is, I will emphasize again, the most widely used method, however. And for most practical situations, the numerical differences in these methods is not too important because your dollar amounts are fairly small. We're talking on the order of cents of differences. If we're talking bigger bond sales, millions of dollars, then it could make a big difference. All right, though in reality a lot of this is just for the purposes of counting, so sometimes it maybe doesn't matter what method you use as long as you do what the government says to do. Here's a graph showing the differences for different values of j, and I've zoomed in so we can definitely see these differences. But it turns out, you look at this graph, no matter what j is, the red and blue graphs are, the difference between them is negligible. Technically the red is the theoretical method, so technically that's a curve, whereas the blue is practical, so that's technically piecewise linear. But I can't tell the difference between the red and the blue. Just looking at these things, they are centered on the same line. I've made them a little thick here so you can see them better. But the semi-theoretical, the green is definitely different. Definitely a noticeable difference on these scales. And again, strange. Because of, for example, here it's increasing at those spots, and when j is large, you get some decreasing spots when it's bought at a discount. Okay, strange interpolation method. It's again most pronounced when j is close to r. I'm getting close to the end of the video here. What I'd like to do now is try to understand this. Why is the difference most pronounced when j is close to r, the semi-annual effective yield rate? Let's consider a fixed t. I picked t equal to 5, but I could have picked something different. And write the equation for the book value with the semi-theoretical method here and enter it here. But then I'm going to think of this now as a function of k and differentiate it with respect to k and think about what that means about the graph we just saw. Now you might be wondering, why is that going to tell us about what we want to know? Differentiating with respect to k. Now what is k? K is representing, again, the fractional part of the moment in time that you're at. It's going to be between 0 and 1 for us in these different pieces of these different graphs. Differentiating with respect to k is going to help us see whether this function, the value, could possibly have a critical point, which would evidently, by these graphs up here, be local minima. Okay? The green graph sometimes has local minima when j is close to r. The derivative with respect to k should help us see that. So here's what the derivative with respect to k looks like. It's pretty nasty looking. You may want to check that by hand again. log, once again, means natural log ln. I differentiated with respect to k. I want to now find the critical point. I want to set this equal to 0 and solve for k. Okay, and when you're doing this, even though there's the j in there, you're thinking about j being fixed here and k being the variable. When you enter this code, it solves, and it's a pretty complicated looking critical point. Now, what's the most important thing to understand about this? I'm going to graph this now as a function of j. Weird. The labels on the axes will be helpful. So the horizontal axis is j. The vertical axis is labeled critical k. You know, this equation here can be used for k bigger than 1 or k less than 0. We're only interested in it when k is between 0 and 1. The formula, this graph here, this formula here, and this graph down there are telling us the function itself does have critical points for different values of j that occur at different values of k. For example, when j is 0.04, the critical value of k is close to 4. That would be where if you took those green graphs and extended them further, you'd see a minimum at k equals 4. But we're only concerned about the values of k between 0 and 1, and that's why I put the dashed horizontal blue lines here. At 0 and at 1, we see that the critical value of k, where the green graph has a critical point, which is a local minimum, is between 0 and 1 when j is approximately between here, which is about 0.048, and here, which is about 0.0525 maybe. That's when this graph, focus on the green graph, has a local min. Each piece, in fact, has a local min. when j is between about 0.048, you can see we've got a critical point there, k, being close to 1 really. Think about each piece here, going between 0 and 1. K would be close to 1, it's close to the right endpoint of this piece of the graph. Just like in this graph, when j is close to 0.048, the critical value of k is close to 1 here. And when j is less than 0.048, the critical value of k would be even further to the right, would be bigger than 1. You see the pieces of the graph have negative slopes the whole time. Okay, the critical value of k is bigger than 1. We don't see it. On the other hand, when j gets bigger than 0.05, up to about 0.0525, we're continuing to have critical points that are closer to where k is 0. You can see them more over on the left in each of these pieces. And once you get past 0.0525 or so, now we don't have any critical points in the green graphs. The graph is increasing all the time. If you extended the graph for other values of k, negative values of k, then you'd have a critical point further on here. But we don't see that because we're only letting k go between 0 and 1. Okay? So I think all this is pretty cool. If you're into math a lot, you might think it's cool. If you're a finance person, maybe you're like, this is not a big deal. But I think it's interesting that you can use calculus and use this technology, this Mathematica, to make these graphs and make these animations and do these calculations for you. Like, I don't want to calculate that by hand. To interpret what we see and try to understand it. And so I hope you got value out of it. And I'll see you at the next video. Or you'll hear me at the next video.